We're all very aware of our circular functions. If you consider the equation here, graphically speaking, its graph is a unit circle. And if I consider an arbitrary point on the unit circle associated with t units, whether they're radians, gradians, or degrees, doesn't make any difference. The coordinates of the point on this unit circle associated with that parameter t are referred to as the cosine of t and the sine of t. And of course, if you pick these two up off the ink board, slap it in for x and y here, you get our first Pythagorean identity, which says this. Well, you and I are experts with these circular or trigonometric functions. So next on my list, you might not have seen these before. My hyperbolic functions are visually described in a very similar fashion. After all, here's the equation of what I sometimes refer to as my unit hyperbola. So let's consider an arbitrary point on the unit hyperbola associated with some parameter t, and we will define its coordinates to be the cosine of t and the sine of t. Oh shoot, I can't do that, can I? Actually, I've already used cosine and sine over there, so I'll change my notation a little bit. I'll refer to this x coordinate as a hyperbolic cosine of t, this y coordinate as a hyperbolic sine of t. Now this really is a way I could define my hyperbolic functions, but to be honest with you, my official definition isn't as such. I just think this is a nice pretty picture, so you can see an analogy with what you had with circular functions. My official formal definition of the hyperbolic cosine of t and the hyperbolic sine of t are given as such. We'll talk about the consequences in a few moments. Now, for the remaining four hyperbolic functions, just to maintain consistency with my ratio and reciprocal identities from trigonometry, I will literally define this hyperbolic function as a ratio of those two up there in this order. Likewise here, and here, and of course here. Let's next tackle the issue of what the graphs of these basic functions look like.